Okay, we're back. So, lesson 7 is circular motion. So, up until this point, we've looked at sort of linear motion and we've looked at things along in one direction and 2 dimensions, but typically things move in sort of straight lines. Whereas now we're going to be looking at things moving around in a circle. And in particular, we're going to look at uniform circular motion. Uniform circular motion. So this describes things that are sort of moving along a circular path but with a constant rate. And it just makes things a little bit nicer. You can have non-uniform circular motion. Say like a car going around a track typically is not moving with constant rate. They might be accelerating or decelerating. Normally tracks aren't perfectly circular either. But just to kick things off with modelling, uniform circular motion is pretty safe bet. Especially when you start going into things and wanting to look at, say, how planets move. If you assume circular orbit, this is where Thomas is going to appear and just shout at me for my wildly inaccurate planetary law behaviour. So, when we talk uniform circular motion, ooh, okay, I'm going to try and draw a circle with this tool. About that, that's pretty circular. We're talking about things that are, say, oh, okay, turn that off. So moving about a circle with some given center. So say there's a particle here along moving along a circular path with some fixed center. So say I'm stood at the center and I'm swinging like a ball around on a string. If you've ever played those games that are like the mini baseball, I'm trying to think what they're called, but like you had like a ball on a string attached to a big stick and you would like hit it back and forth to each other. That sort of thing, right? Like it would swing around in a circle. But the particle itself is trying to move in a straight line. Things generally don't have curves to them. Think bodies in motion stay in motion, bodies at rest stay in rest, unless acted upon by a specific force. The particle, that purple like ball, wants to move in a straight line, but it's being pulled in by something towards the center. And the reaction of that force pulling it in and its motion in the other direction gives it this circular motion. So that's potentially something being spun around on a string. Potentially that's something moving within a fixed cylinder. If you've ever seen the really cool trick that you can do with picking something, like picking a ball up without touching it, of holding I think it's like a wine glass and an olive is the example that comes to mind in my head, and I don't know why. But you can like start spinning it round and it'll like move within the rim of the glass and it wants to fly outwards. But it's contained within the glass, so it has to move in that circular motion. So if I were to write some words about this, it would be: consider a particle attached to a light, inextensible string. String being swung around at a constant rate. Okay. Though the particle moves, that weirded me out then. So though the car particle moves around a circle, its velocity is instead tangential to the circle at the point where the particle is located. So what that means is, as I've sort of drawn it, not only is that velocity moving sort of in a straight line away from the circle, away from the center, but actually this makes a right angle with the radius. So it's moving for some r here. So the velocity, if we say let go of the string, what would happen is the particle would move perpendicular. So it would move in that direction the velocity vector is pointing. And this is actually where like discus and I'm trying to think, is it like hammer toss? If that's the right one. The old school Olympic sports, like athletic sports, where people are holding heavy things and they want to throw them really far. They'll spin in a circle, and if you notice, they let go. Discus, thank you. They let go when they're stood sort of at a right angle to where they want to throw. So if I want to throw forwards, I'd let go when it's like here to me, because it's going to fly off tangential to sort of where I'm facing, where I'm letting go, which is quite cool. Like a fast hamster in a wheel that falls out. Like, sort of? Just kind of accidentally goes flying. Arguably, this is assuming no gravity for the minute. That adds all other things to this. But yeah, as a reminder, that arrow with a V is the velocity vector. It has a size and a direction. So the direction that it's pointing, not only is it perpendicular to the string that I'm holding that particle attached to the center with, but it's also going to be rotating. So wherever the particle is, if the particle at a later time is here, then my velocity vector now points this direction. Okay, so it moves around. So if we let go of the string, if letting go of the string causes the particle to fly off in the direction of the velocity vector,
it is funny that April Fool's is the one day in the recent month where I am able to catch the stream.
No comment. Thank you so much for the resub, Tech. Hello, lovely to see you. Yeah, I don't know what it says about me that my mods appear during April Fool's. Again, I should have done something more intelligent with April Fool's. However, we get what we get. Thank you so much. Okay, so if letting go of the string causes the particle to fly off in the direction of the velocity vector, then a force must have been acting on the particle to cause the uniform circular motion. And this is coming from Newton's first law? Luckily, I have loads of notes about Newton's laws that we did in lecture 2. It's one of them. You're right, it doesn't matter, but we should. Yeah, Newton's first law, which says bodies at rest or in motion remain at rest or in motion unless acted upon by an external force. Quote you to the examiner, it's one of them. You know for a fact that on like every exam mark sheet, whatever, it's going to say that you can't, you have to specify. Like, this number 1 is specify which Newton's law or Kepler's law you mean. But yeah, so if nth law, where n is a number between 1 and m for m bigger than 3. Bigger than or equal to 3. He might have more laws, we don't know. Maybe he had a law that he never wore yellow socks. I don't know. But yeah, so basically what that's saying is if you spin something round and you let go and it flies off, it means that the spinning round must have caused a force acting upon the particle. This force could be a string pulling inwards, or a wall pushing the particle around, for example. So, yeah, exactly. There could be also less obvious forces that cause this effect. If you're in a car that does a sharp turn, you feel a force affecting you. Like the car is affected by the wheels turning and the steering, but the steering. But you personally feel a force pushing you outwards. So regardless of source, the force is called, this is where I always get it wrong, but I'm pretty sure, centripetal force, which is directed towards the center of the circular path. So going back to our example from before, let's chuck this again down here. We would have a force acting inwards towards the center, F there. Shemai, Sadachi, how are you doing? How is it going? Oh, let me move my notes. Okay, so that force is pulling inwards, which makes sense if you think about it. If you have the velocity moving you forwards, you have a force pulling you inwards to the right or to the left, you're going to turn. It's a turning force. If we were going to go back to sort of resultant forces, it pulls in that way. If it was the other way, it would be a turn towards the other direction. Love some circles. Love some circles, me. Okay. Since the force acts inwards, there must also be an acceleration acting inwards towards the circle center too. Okay, and this is where we get to site N2, which is F equals ma. So because there's a force and we're assuming that there is mass, there must be an acceleration. Yeah, so this is the weird bit where if you're a point and you're in a car and it goes round, there is a force acting inwards on you, and the car turns, it's heading in this direction. But you sat in the car, say this is you here, you feel a pull outwards. All right, if I turn sharply to the left in my car or in a roller coaster, or if I swill my glass or something happens, there's a sharp turn to the left, the things inside of the glass, the things inside of the car, the things inside of the roller coaster are going to feel a pull to the right. And I realize that it's opposite is what I'm trying to say. And that is due to the frame of reference, because the car is pushing one way sharply, it's moving me, and I get that reaction force. So the feeling of a force, it would help if I wrote where you could see. The feeling of a force pushing outwards when taking a sharp corner is due to the reaction force, which N3 between car pulling inwards and yourself. And with that, we've just covered Newton's first, second, and third law in like page and a half, which is quite fun. I love that for circular motion. It uses all three of them. So this is chemistry. Ah! No? I don't think this is covered in chemistry. I might be wrong. It's been a long while since I've done chemistry. Okay. It is feeling very physicsy at this point, though. Yes, it's getting very physicsy. Okay, so how do we make this mathsy? Let's introduce the maths. The maths. So, since motion is circular, it now makes sense to describe things with polar coordinates. So, quick recap. When we describe things in our sort of normal plane, so xy or xyz, okay, these are called Cartesian. And they describe, each coordinate describes how far along you are within a given, so you go x along horizontal, y along vertical, and things move in sort of horizontal and vertical directions. So everything's at nice 90-degree right angles to each other. In contrast, when we describe things in polar coordinates, what we're doing is we're saying for a given plane, so let's pretend we're still on the xy coordinate for the minute. We have an origin and we have our point. We now describe things as its direct straight line distance between the point and the origin and the angle away it is from some horizontal. So here your coordinates would be xy, and here your coordinates are r theta. And there is a 2D to 3D equivalent. This is a 2-dimensional version. The 3-dimensional version, when things are being swung around, we can do things differently. So we can either say they're cylindrical, where we just add the z in and we just have like a cylinder, or we leave it alone. And we have spherical, where we have 2 different angles. Don't worry about that in the minute. We're going to stick with 2D polar for the minute. That's 2D, and that's 3D. There. Okay, so what does that do with us? Well, we're talking about things moving in a circle, and we have our point, so we can define our origin here. We can define our radius, is how big our circle is, and then it's on us to set what some fixed horizontal is. Normally it'll make sense, or it might be between 2 points, and we have a theta. So as long as whatever we fix our frame of reference is to be horizontal, we're fine. My favourite name dropping of chemistry was when my partner expressed surprise the juice carton was expanded slightly after being left on the counter for a minute or so. It's the ideal gas, Lawrence. Oh dear. Hate polar coordinates. I love polar coordinates. I think they make me very happy. I think things start breaking down when you need to describe basis vectors, but like polars are just chef's kiss. Okay. So when I talk about theta, I talk about an angle with respect to some horizontal, and when I talk about r, I talk about the distance, the size of the circle, the radius of the circle. Okay. Don't know why I did that there. Get off. Has anyone sussed out what music I'm playing yet, by the way? Because, like, there is not enough excitement about this. So. A particle moving with constant speed This is indeed Lo-Fi Chapel Roan. How freaking cool is that? It's so good. They make sense to me enough, but when I use 3D polar with two angles trying to do atomic physics at the same... Yeah, that's... No, don't want to. Can't make me. Spherical is not the nicest. The worst one I have seen at the minute is one of my collaborators uses Euler angles, and we basically agreed that I just don't have to think too hard about it because it upsets me, but... Yeah. I just think everything is cute lo-fi. Like, it just makes me happy. Okay. A particle moving with constant angular speed omega is at an angle theta to a reference horizontal. What does that look like? Looks something like this. Okay. So now omega, which is our angular speed, is curving around with it. It's no longer in a straight line. It's talking about the speed as we move around. So our rotational speed, our angular speed, is fixed. But the angle that we are to our fixed horizontal is going to change. So is shown below. The angular speed is given by radians a second. Ooh, nowhere near enough space for that. So this is rad per seconds. So radians are, there are pi radians around a circle. Is it pi? No, 2 pi. There are 2 pi radians around a circle. Yep. Rather than degrees, which there are 360 of. So they're a bit more chill. But the equation for the speed, omega, is the rate of change of the angle. Okay? So as the faster that the angle is changing, the faster the speed of the particle as it moves around that circle. And in mechanics, the way we write ddt as the rate of change of time is a dot over it. Okay, so dot notation is usually, I can't say usually always, can I? Time. Derivatives. So that gives you a relationship with how fast that angle is changing. And obviously it hits a point and then it comes back to itself and it starts again and then it goes round again and then it goes round again and it'll always reset to 0. So we're stuck in a periodic rotation, but the rate of change of that is the speed. The distance traveled. So now we have speed and we have time, so we're going to have distance in there as well. Between the horizontal and the point P, is given as arc length. Denoted by S, where, so the equation for arc length, S is r theta, where r is the radius of that circle and theta is the angle to point P. So that gives this here as S. And again, S is going to change as it moves around in a full circle and completes a full revolution. it's going to get bigger and then get smaller again. So as theta changes, so S is also going to be periodic. One more equation. The linear speed v of the particle. So this is going back to that original all the way up here. This v, so linear speed, so in a straight line, so at a fixed point in time, if I freeze frame it, it has some velocity vector pointing forwards, because vectors don't curve. She's pretty sure. Which is just the true rate of change of S now. So rather than rate of change of the angle, we're doing the rate of change of the arc length. So that size difference is given as. So the equation for the speed is the rate of change of the arc length, ds dt, which is the rate of change of r theta. Now, for uniform circular motion, the circle isn't changing size. It's a fixed size circle. Obviously, if the circle is changing, I can't do what I'm about to do. But because r isn't a function of t, I can take it out. So I can do r d theta dt, which is equals to r theta dot. And the rate of change of theta dot is omega. So r omega. So it's basically a really long way of saying, i.e., the linear speed is the radius times the angular speed. Linear speed is radius times angular speed. Right, again, note this isn't velocity. Okay, really important to remember. Velocity is a vector. It has a magnitude and a direction. The direction is constantly changing. So the linear velocity is constantly changing. But the speed of that is fixed. So the magnitude is going to be fixed because omega is a fixed value, r is a fixed value, so v is going to be a fixed value. So the velocity changes because the direction changes, but the actual magnitude of it in our case isn't changing. Okay. Since the force always acts towards the center of motion, it is constantly changing direction. Okay, so if I'm at one side of the circle, it's pointing towards the center. If I then go to the opposite side, it's still pointing towards the center. So in terms of like our Cartesian, our fixed frame of reference, looking outside inwards at the circle, it's pointing in two different directions. So here, F is moving inwards. Here, F is moving inwards. Here, F is moving inwards. So it's just always moving towards the center of the circle. So F is changing direction. And if F is changing direction, don't know why that has an R in it. Changing direction. then the acceleration must also be changing direction. Okay, so we have the equation for acceleration in this case. A is given as v squared over r. Now v squared is omega r squared over r, so that's omega squared r. This must be non-zero. Why? As it describes the change in velocity. So the sneaky thing that I sort of am omitting here potentially is that this is a vector, that's a vector with these equations. Which is constantly changing. So the velocity is constantly changing direction, right? So the acceleration is constantly changing direction. So the acceleration has to be non-zero. Now, it could be net zero, but the magnitude of it could be zero, in which case it wasn't moving, because there'd be no force applied on it, which would stop it moving in a circular motion. So it's very chicken and the egg almost, because you're in circular motion, you must have force making you be in circular motion. It sort of depends which assumption you make first. What is interesting about this equation, though, if we do another note, A equals v squared over r means A is proportional to 1 over r. So for a fixed velocity, a shorter radius, a smaller value of r, will give a higher acceleration. So the acceleration required and the radius of turning are going to be inversely proportional. So what does that mean? Well, for the same velocity, the same linear velocity, smaller goes faster when it's moving in a circle. And this sort of makes sense if you ever think about the centripetal force demo, where if you ever have someone like stood on a turning circle on like a platform and they hold their arms out wide to the side and then pull their arms in, you shorten your turning radius by pulling inwards and you speed up. And then when you put your arms out again, you slow down. That is entirely due to that relationship. A is proportional to 1 over r. Similarly, if you've ever seen the sort of trick of if you put a disc that's rotating and you track where the bottom of the disc is versus where like a third of the way into the radius is, even though you do a full rotation, that center point is going to be, I'm going to draw this out because this is hard to explain. So if you have a track and you have a circle, say like a disc, and I keep track of, say, where this point on the disc, how it rotates, and I keep track of where like this point on the disc where it rotates, and I watch it come through. And it will move if I do one full rotation. So I start rotating this, and it's going to move along in space, and eventually it gets back to where it started. There's a nice little paradox, or like brain confusion paradox about this, where the outer one, they've moved essentially the same distance. I think this is actually a different paradox if I try and think about it. Thank you for the follow. But yeah, so the one on the outside has moved technically a further distance because it's travelled around that circle, a longer circle, right? It's tracked a bigger path. But the distances linearly are exactly the same. It's a nice little confusing relationship there. But essentially what's happening is as you're turning it, the inner one is moving faster because it's going a shorter distance. And that's because of that. Thank you for the follow. Welcome in. Okay. We're just going to take a quick break so I can refresh my water. And then we will be back and do some problems. Think of the fact how long you're in tests. That, yeah. Quite long. Right, I'll see everyone in like 5 minutes. Bye. Hello. Okay. So this next bit is a little bit of a cheat sheet of types of circular motion. Types of circular motion. So this is sort of like I had this in my A-level notes when I was doing my A-levels, of just all of the different questions and what sort of forces you need to think about when you're talking about each one. Because obviously some of them, as we say, you have that centripetal force pulling you inwards. That can be along something physical. It could be just felt by an overarching effect that doesn't necessarily feel like a string pulling in. So we'll see a few different examples. So first up is particle on a string. If I can spell. So this is your classic, say you have circle, actually let's draw what's physical and then add in the motion. So you have a string and you have a bead on a string, or a point on a string. Then the motion is sort of going to be I'm intentionally trying to draw it elliptic and it's just not working. There we go. Fuck it. That way. Ish. If in doubt, go for the tool generator. So we have a string and we have our particle. The forces that are felt here are going to be tension working inwards. You're going to have some sort of reaction force upwards. And then, that's why I was trying to draw it downwards. So if you're swinging this horizontally, you're also going to have gravity affecting it. So if I were to swing something, I don't know what's going to be. This would be where I would have thought about having a demo. Unfortunately, I don't. I have a very small bit of string. That I can tie knots into to make a sort of particle. Okay? So if I have a string, if I swing, come on. There we go. So it's moving in a horizontal direction. Now on the particle, you have tension in the string as I'm spinning it, but you also have gravity pulling the particle downwards. So the decay of motion, instead of being horizontal, moves downwards. If I swing it vertically, it's a lot easier to do. It's very hard to see, but it's a lot easier to do because on the downswing, gravity is working in my favour, so it's affecting part of the motion. Problem with swinging things vertically is this is no longer uniform circular motion, or the force that I have to put in is uneven depending where it is on the rotation. So typically this would be in a plane horizontally with a uniform force felt the entire way around, moving downwards. And then you'd have the reaction force upwards as well. If you were going to have sort of a bead sliding around a wire, it would be the same thing, but instead of a tension in a string, it would be a reaction force of the bead on the string. So equivalent bead on a wire, where again you have sort of something moving in a plane, and now you have, say, a tube. Let's see how good my drawing can be. Okay, so here, okay, if you have some, I could have just drawn a full circle and drawn over it, oh well. If you have a bead moving around, you now have a reaction force between the bead and the string and the wire moving in. Again, you have gravity acting downwards, and you'd have a normal force to gravity moving upwards. Particle on a rotating disc. So if you have a disc that's rotating in the horizontal and you have a particle load on it, like sat on the disc here, and this could be more similar to sort of car on a track type motion as well. My particle is going to be a square here, where this thing is moving sort of that direction. Once again, you have gravity going on, and you have your reaction force. Now you have friction holding it in. Okay, so friction is the thing that's holding the thing in place. If it was a completely smooth, frictionless surface, a completely smooth surface, the particle would sort of stay where it was as the path moved underneath it. But it's friction that's holding them together, that's pulling it around with it, and that's what's throwing it away. Here, it is good to note the particle will slip when F greater than equals mu r. So once it hits that sort of frictionless, back when we did Newton's forces, if the force is bigger than the frictional maximum, it's going to start slipping down the track. Here it's going to start slipping either outwards or inwards. If it's a car on a bank, okay, now you have an added angle in sort of here. So say we're moving, this is sort of the side view, but the top view is again so it is circular motion, but now it's just on an angle. You again have gravity, you again have friction. Now your normal force is at an angle. If you go too fast, it will actually slip upwards. If too slow, it will slip down. So this is where I was saying at the start of the stream, you can have a glass that is spinning enough that you can actually pick up the olive because it curves outwards. It's on a very steep bank. But if you spin fast enough, you can actually slip up the bank. And there's this trend on TikTok that I've seen at the minute of people in a sort of ice ditch. And it's like, try and get out of it, basically. It's this curved like hole, like a semicircular crater. And the trick is to run in a circle, because if you try and run straight up, you're going to slip back down. The friction's going to take over and it's going to pull you down with it. But if you move in a circular motion, you're able to like use the friction to your advantage. You're like able to like actually start moving upwards, which is perhaps counterintuitive, but a very cool thing to do. And the extreme of that is then inside a cylinder, where you now have, say, the cylinder is rotating. So if you've seen those arcade like theme park rides where you're just stood inside of a cylinder that's rotating and you're not holding on to it, you're not like strapped in, you're just like holding on, that spins fast enough that it throws you backwards. Similar sort of thing. So now friction moves up the cylinder, gravity moves down. And again, you have your reaction force is actually now your centripetal force, where it's pushing you inwards. It's the feeling of the wall behind you pushing you forwards into the center of the circle. If you were vertical, you then have to account for gravity in this one. Then you get I just write it out and then I'll explain. So they say gravity is sort of helping me on one side and not on the other. So because my velocity is non-constant, you have sort of a potential energy that's higher at the top than it is at the bottom, and you have a velocity that's higher at the bottom than it is at the top, and it balances out. So you need to consider those. Right, so we have one end of a light inextensible string, stop it. Ah! Oh, please tell me I didn't just delete that. Oh, that's really upsetting. Well, that's infuriating. Give me 1 second again. We have one end of a light inextensible of length 2L is attached to fixed points A and B with AB equals L. So the distance between them is half the length of the entire string. A ring R of mass M is threaded to the string and made to move with constant speed V in a horizontal circle about B. The string is taut. A, show that B, the length BR is 3L over 4, and then B, given air resistance is negligible, find the tension in terms of M and G. and then find B in terms of G and L. And then we're going to click off that, click off that. Right, there we go. So first things first with these sorts of things is we're going to draw it out. So we have, firstly, that they're vertically above each other. So we have our point A, and we have our point B, and we now have that gravity is in the system. Okay, so because we're looking at a vertical system, we have gravity involved. We have this vertical distance is L, and we have that a ring of mass M is threaded and made to move with a constant motion. So the string is pulled sort of pseudo-taut. And here there's some ring R with a mass mg. What do we have? So we have that is a right angle. So because it's moving horizontally about B, we have that's a right angle. And because it's pulling the string taut, realistically, this is as if I've threaded something on a string and I'm pulling it so it's in contact. So it's going to be holding it tight. So there will be tension here and here, and it's going to be the same value of T in both of those directions. So first of all, we need to show that the length BR is 3L over 4. So R and B are expressed in a circle. So if we take this triangle in its entirety, okay, we have B, R, A, and we have that AB is L. We know that for a fact. We know that AR plus BR is 2L, because that's the length of the string. And we know that BR is some radius of a circle R. Okay? So that gives us, this is L, this is R, and we can actually write this side by rearranging this second equation here. AR is 2L minus R. Okay, and the question is find R here. Okay, so find BR, B capital R. So we can use Pythagoras. If in doubt. So that just says that A squared is B squared plus C squared. Because we have a right angle, we can do this. So we have that 2L minus R all squared is equals to L squared plus R squared. Expanding the left-hand side out, we get 4L squared minus 2 lots of 2L R plus R squared is L squared plus R squared. Immediately I can cancel through the R squareds on both sides, and that gives me 4L squared minus L squared. I'm going to take that right-hand side over. Okay, is equals to, and I'm going to take this side over as well, 4LR. So I get 3L squared is 4L squared R. And then I can cancel the squareds. I can cancel the L's through. Interesting. No, not squared. That's why. For LR. I can cancel one L from each side and then divide through by 4, and that gives me 3L over 4 is equal to R. So BR, which we defined as little radius, is 3L over 4, as required. Okay, and that's just from using the geometry of the system. So because it's pulled in a circle, it's flat along the bottom. The only thing the top bit of string between A and R can do is be taut, so it has to be a straight line. Okay. Then we have, given the air resistance is negligible, find the tension and find the speed that it's moving around in a circle with. So, find the tension in the string. Let's look at the ring first. So we have essentially this going on. So we have a value T, and we have mg here. And there's some value alpha here, okay? Now, these are all of the forces acting through this ring. Due to Newton's third law, we know that they're going to have to balance. So I'm going to be able to eventually break them down into breakdown, just good advice in life, into vertical and horizontal. Okay, so looking at my vertical components first, I have mg going downwards, and then upwards I have a component of this top, like this angular value of t. The horizontal one is just horizontal, but that one at an angle is going to have some horizontal component and some vertical, and it's t cos alpha in the vertical. In my horizontal direction then, I have nothing going that way. Sorry, in my horizontal then, I can do F equals ma. So I have my acceleration and I have my forces balancing. So that's going to come in a minute. I have one equation and one unknown on the left, so I can focus on that one. So just looking at this vertical equation again, mg is t cos of alpha. And remember, alpha is this angle here in a triangle that is L, 3L over 4, and this was 2L minus 3L over 4. So I can work out from SOHCAHTOA, which if you haven't seen before is how we work out sine, cos, and tan of an angle with hypotenuse, opposite, and adjacent. So I get cos of my angle alpha is equal to 3L over 4 over 2L minus 3L over 4, so 5L over 4. So cos of alpha, cos of alpha is 3 over 5. So that gives me mg is t 3 over 5, or more usefully, t is 5 mg over 3. Okay? And that just is the tension in the string now. So that value of t is also going to be working in my horizontal direction. So when I go to my horizontal direction, I have in the inward direction, I have t plus t sine alpha. So these are my forces that are acting on the ring. And then I have mass times acceleration. So I have 5 mg over 3 plus sorry, my throat is starting to go. Plus 5 mg over 3. Sine alpha is going to be 4/5 from doing the same argument as before up there, is m, and then acceleration here is my v squared over r value. So I could have used omega r, but I don't have an omega in this, so I'm not going to worry about it. Then we just have to solve. So we have a 5 and a 5 here. We have an m in everything, so we can get rid of those. That's fine. Our r here, we can substitute for 3L over 5. So we've got 5 over 3 plus 4G over 3 is equals to v squared over 3l over 5. 3l over 4, sorry. This is why we should go back and check things. 3l over 4 from that BR value. So that gives us 4 over 3l, 5 over 3 plus 4g over 3 is equals to v squared. So what do we get? What do we get? Ah, no, sorry. Oh. Don't do that. 3l over 4. This is why the fractional notation upsets me, is because I just make mistakes. So we can divide through those 3's. So that's fine. So we get 5 over 4. I'm missing a g from there. (5g plus 4g is 9g over 4 with an L is equals to v squared. So that gives me v is the square root of 9gl over 4. Those two fractions, those two numbers are squares, so I can get 3 over 2 square root gl. And that's this velocity, that's the speed that it's moving around with. Ta-da! So, to summarize, coming back up here, we looked at uniform circular motion. So that's things moving with constant rates in circular paths. We talked about the fact that there is a linear velocity moving you out of that circle, so there has to be some sort of force pulling you inwards. And that is due to Newton's first law. Newton's second law then tells us that there's also an acceleration, so F equals ma is happening, so an acceleration is also moving inwards towards the centre. And then we also have the feeling outwards force as we turn a corner on, say, a car or something, is due to the reaction force. So this is why you'll see cyclists lean in, whereas car drivers lean out. It's whether you're feeling the force of the turn or the reaction force of the turn. So it's whether you're the thing that is doing the turning or being pushed against the thing that is doing the turning. Describing things mathematically, we talk about polar coordinates again, had a nice little recap of that, and we started to define some equations. So angular speed is rate of change of angle from some fixed reference. So set something to 0. How fast are you changing what angle you're at from the centre? You have, I'm so sorry, we're just doing a summary. Luckily, it'll be a VOD and it'll also be on YouTube sometime this week, probably next Tuesday. We introduced arc length as a distance travelled between that fixed horizontal reference and your point. And then your linear speed is your rate of change of that arc length. So again, you get this relationship between angular velocity and angular speed and linear speed, which gives just the radius multiplied. The acceleration points inwards, so you get this angular velocity relationship and this linear velocity relationship, and both of those give you that in a linear case, the acceleration is inversely proportional to radius. So moving things inwards is going to make it go faster, or relatively faster. I got confused by a paradox. We looked at different types of circular motion, so particle on a string, beads on a wire, basically just checking how you call those forces. It's always a force acting inwards, that centripetal force is always a force, but is it tension in the string? Is it a reaction force from something acting on you? Is it friction due to something underneath you holding you in place, or a wall holding you in a certain vertical direction? And then we did an exam question that had 2 fixed points above it with a long string in between and a tension, or a ring being moved in tension, and finding all of the terms of that, and did some sneaky Pythag, because there's always some Pythagoras in all of these problems. And that covers that. So, only thing left for us to really think about in this series at the very least, which will be next stream, is more complicated dynamics, and in particular we're probably going to look at simple harmonic motion, which is a nice extension from what we've been doing today.